Welcome to Monday, everyone, and thank you so much for showing up for your learning. Yeah, that's right. We're going to get radical today a little later when we have a quiz. But for now, we're going to be we're going to keep it in the family. We're going to be looking at families of quadratics. All right, and there's a family of quadratics. What this means is that our quadratic is going to share a common characteristic. It's a group of parabolas. It's a group of quadratics that all share something in common. Like in my family, we all love Peppa Pig. We're all just big Peppa Pig fans, and that's the trait that unifies us. Okay, I'm taller and my wife is shorter and my kids are shorter than all of us. So we're all different in our own way, but we all share something essential. Now, go ahead and factor these, put them into factored form, and see, what is a common characteristic about f of x, g of x, h of x, and j of x. And then we're going to pause and then pick up the video. All right. Oh, a tissue. So you've had a chance to factor these. So let's take a look at what you got. So this is what I got, and let me know if you have something different. Because well, don't let me know. Just let's take a look. In every case, when I factor out this a, I end up with a parabola that has the same factors in there. X squared minus 3x minus 10. So I'm looking for two numbers that multiply to negative 10 and add to negative 3. Those numbers are negative 5 and 2. So that's what it looks like in factored form. When I factor out this negative 2, I end up with x squared minus 3x minus 10 in the bracket there. So you have to take a negative 2 out of there and a negative 2 out of there. It recreates those terms. So would all these parabolas be the same or would they be different? If we threw them into Desmos, would be the same or the different? Yeah, they'd be a little different. Siraj, how would they be similar?
They would be similar because they have the same x.
They would have the same x-intercepts. They have the same roots, but they are different because of their stretch factor has changed with each one. So they have a common characteristic. That common characteristic is the roots. Now let's carry on. So this is the factored forms of all of these that we've worked out. Fantastic, very good. And notice that the roots are all the same. The roots are positive 5, because positive 5 would make f of x equal to 0. Oh, sorry, the answer should be g of x, h of x, j of x. And here, also, x is negative 2 is another root. So we have to remember to flip the sign to get the roots. So here are those different parabolas. These are all the graphs of them. And we notice that with different stretch factors, we can hit different points outside of those two roots, but you notice that they share these roots. Okay? So there is negative 0.5, that parabola. Here is a negative 2, that parabola. Here's positive 4, that parabola. And there's the parabola just with an a is equal to 1. Looks like that. So they differ in their stretch factor. So now let's determine the equation of the family of quadratics that have x-intercepts at x1 is equal to 4 and x2 is equal to 2. So here is x2 is equal to 2 and x1 is equal to 4. So we want roots there and there. And we want all the parabolas that will do that. So how are we going to do that? How are we going to create this family? Well, we use what we know about the factored form of the parabola, and we can just input it there into this function, into this formula. So I could rewrite it as the family of functions of x is equal to the stretch factor multiplied by x minus the first root multiplied by x minus the second root. So what am I going to put in here and here? 4 and 2. So minus 4 minus 2. Could I have done minus 2 and minus 4 instead? Yep, that would have been fine. This will give us, and we can sketch some. Here are some parabolas that we could do. Here's one parabola, and it's going to come down and hit there and turn around and go up. All right. Sketch another one with a negative a. It's going to come up and then come down. And then sketch one with a really negative a, something that's going to do this. Right? Just get the idea that there's a variety of parabolas going through those 2 points that share those points, but that have different stretch factors. We can flip them in the x and y. So with a negative a, we can make it a bowl collecting rain or an umbrella shielding you from rain. and we can make it stretchier or flatter. Great. What if A is 0? What kind of shape do we have? Yep, it's a line. And if A was 0, it would still go through these 2 points. It would be the x-axis because you would have f of x is equal to 0. It would be the line y is equal to 0, which is the x-axis. So we can even turn a parabola into a straight line with a stretch factor of 0. And actually, that connects to your y equals mx plus b. Your general form, your standard form of a quadratic, ax squared plus bx plus c. If a is 0, it's just a line. Make sense? All right, let's carry on. That's a little bit outside of the lesson. Now, if we have radical roots, this is really cool. If we have radical roots, what's our function? Oh, another thing. Let's turn this into standard form. How do we do that? Let's go back a second. We want to turn this into standard form. How do I do that? How do I turn the factored form into standard form? We've been practicing going the other way this morning. Suraj? Yeah, just FOIL it. Expand and multiply. There, boom, boom. So use your FOIL rule. So I would have this function of x is equal to a multiplied by x squared. X times negative 2 is minus 2x minus 4x plus 8. All right? Collecting these like terms in the middle gives us a times x squared minus 6x plus 8. I love it when they have 6x in there. It makes me feel like I'm successful. All right, so we've been successful at turning this into standard form. If we really wanted to go another step towards standard form, it would look like we would expand this a in. Ax squared minus 6ax plus 8a. And that would be the family of quadratics that would always go through these 2 roots and that we could stretch all over the place like that. All right. Yeah, so we can take a look at that Desmos later, but we're a little tight for time. Now let's take a look at one with radical roots, and this is going to be a nice review of our radicals. We have a root at 3 plus root 5. So root 5, about what is that? It's bigger than what integer? It's smaller than one integer and bigger than another integer. What integers is it between? Root 5. Is it smaller than 3 or bigger than 3? Root 5. Smaller than 3, yes, and bigger than 2. So we know that 3 plus root 5, it's going to be like 3 plus 2 plus a little bit. Okay, so it's going to be out there. So you can just kind of sketch it on there. It's closer to 2 than it is to 3. It's much closer to 2 than it is to 3, root 5. Okay, and then 3 minus root 5, well, that's like 3 minus 2 and a bit. So I go 1, 2, 3 minus 2 and a bit. So it's going to be also there. So I'm looking for the family of quadratics that have those roots. Okay. Now, how am I going to do that here? Well, I do the same thing as I did up there. It's just more complex now. I have to put in this and that. So let's go over here. F of x is equal to a multiplied by x minus the first root minus 3 minus root 5. Oh my goodness, am I running this pen into the ground too? Okay. Minus both of them because I have to subtract both of these. Where's my other pens? Here, equipment malfunction. I'll use a better pen anyway. And I'll write this a better way. So this is x minus bracket 3 plus root 5 and bracket. And then I have x minus 3 minus root 5. I need the 3 plus root 5 and the 3 minus root 5 in there. And then I can carry on. Now, if I want to expand that, well, let's bring this negative in. This is going to be is equal to a multiplied by x minus 3 minus root 5. And this one is x minus 3 plus root 5. Okay. Notice that my plus minus is opposite there. Now, how would I expand that into standard form? It's like FOIL, but with another letter. I now have 3 terms in here. And so 3 terms times 3 terms, I'm going to get 9 terms, and then collect the like terms. Oh, I see some people shaking their heads at me like, Mr. Jennings, that was complex already enough. And now you're making it more complex. So let's just put in our arrows, and that'll remind us. This x needs to multiply by x, needs to multiply by -3, and it needs to multiply by positive root 5. And then this -3 needs to multiply here, here, and here. And then this negative root 5 needs to multiply here, here, and here. Okay, we're going to get 9 different terms coming out there. And I'm going to need another piece of paper. So I'm just going to expand this on a separate sheet of paper. Copy it out. Whoops. This is x minus 3 minus root 5 multiplied by x plus 3 plus root 5. Oops, so it's minus 3 plus root 5. Sorry, I got to get those signs correct. I often make sign errors, and that's no good. So then let's work that out. That's equal to x squared minus 3x plus root 5x. Negative 3 times x is minus 3x. Negative 3 times -3 is plus 9. Remember, that's a negative. This is a negative. This is -3. And then -3 times positive root 5, that's -3 root 5. Okay, now I do these root 5 terms. Negative root 5 times x is negative root 5x. Negative root 5 times -3 is positive 3 root 5. And then negative root 5 times positive root 5. What's negative root 5 times positive root 5? Suraj, -5. Root 5 times root 5 is 5. Because the root of 5 is give me a number that when multiplied by itself gives me 5. That's the definition of square root. So the square root of 5 times the negative square root of 5 is -5. Okay. Now I have all my 9 terms. Count them. 1, 2, 3, 4, 5, 6, 7, 8, 9. Now I get to collect my like terms. Okay. X times x. Yeah. So there I have x squared. It's my only x term. My only x squared term. -3x plus root 5x minus 3x minus root 5x is minus 6x. Notice the plus root 5x and the minus root 5x cancel out. So I only have negative 3x and negative 3x together to make negative 6x. Okay. Now, count my constant terms. Plus 9 minus 3 root 5 plus 3 root 5 minus 5. So what's that? It's plus 4. Done. Final answer. If it helps you here, you can circle your x squared terms in one color. You can circle your x terms in another color. And then the rest are all just, where's the A? Oh, I didn't have the A here. I would still have the A there. So when I'm transferring this up here, I will say that, this is equal to A times x squared minus 6x plus 4. And that will be the family of quadratics that goes through these 2 points. So that's with a radical root. So expanding with a radical, I just wanted to highlight that you just use your FOIL rule, except now you have to remember that there's 3 things times 3 things, so I will have 9 things. Dave? The x's with the root x's. Let's take a look at the x term here. How did I get to -6? So negative 3x plus root 5x minus root 5x. So plus root 5x minus root 5x is 0. So those cancel. And I have negative 3x minus 3x gives me minus 6x. And that's all of them. They're often going to cancel in these types of problems because of the way the problem is set up. And because of the quadratic formula is going to create these types of things. If it wasn't, then you would just have like -6x, -6 plus root 5 or something like that. You would just write it out, however it was. You still just collect. So now, let's take a look at how we can use this to find a specific quadratic. Oh, wow, you are all very patient. We went right over the break. So let's take our break, and when we get back, we will finish. All right, everyone, let's try and get done what we can get done before the fire drill. So here we have one of my favorite problem types. And this is a problem type that you can use to practice your math skills. And it doesn't even need to be this simple. You can make it very complex for yourself. So if you're one of those people who sits in math class and says, this is boring, I can do this. If you want to challenge yourself, give yourself 3 random points. 3 random points, and see if you can put a parabola exactly through those 3 points. 2 points define a line. So there's only one line that goes through any given 2 points. You can only put one line through it, right? 2 points, only one line. 3 points defines a parabola. And you can do this. And I can show you how to do it with 3 general points. Here we're working with 2 special points. We're starting with the 2 roots. And then we're going to give 1 more point. That's going to fix the parabola. That means there's only one parabola that goes through these 3 points because we have 3 distinct points. So here, we're back to this section where we have y-intercepts at 4 and 2, and we went back a little bit. There we go. Equation. So we now have x-intercepts of 2 and negative 3.
Good morning, CCI. This is going.
So here we have 3 points. Okay, so let's focus in on here. We have 3 points. This point, that point, and we want to pass through the point 0, 3. Okay. So we have 3 points. That defines a quadratic. So let's take a look at what quadratic we're going to define and how we would do this work. So anyone have an idea of how we would do this, like right away, without me doing it myself? Do you know how to do this one? No? Siraj, what's your workflow? Yeah, we're going to input the x-intercepts first, and that's going to give us the family of quadratics. We're only going to have one unknown. And that the only unknown we're going to have is a. So when we have one unknown, and we know what the output we want, the output is 3, and the input is 0, x is 0. So we know that we're going to be able to calculate our a. So we just want to be able to like predict our solution path. It's going to be similar to solving like a systems of equations or something, except we only have one unknown. So here, the first thing that we're going to do is create our family. So our family is going to look like f of x is equal to some stretch value a multiplied by x, subtract the first root. So the first root is 2, so we're going to subtract 2. And then x minus the next root is minus 3. So we're going to have x plus 3. And that's the family of quadratics that will go through the points 2 and negative 3. Okay, so that's all of the quadratics that will do that. Some of them look like this, and some of them look the other way, like this. And there's an infinite number of quadratics that can go through there because there's an infinite number of a values. Now, we know that we're looking for the one quadratic that goes through this point, and we're going to find that when we have 2 points, we still have an infinite number of quadratics that it could be. But as soon as we add one more point that's different, okay, so there we have the point 0, 3. Okay, then we know that that's going to give me only this quadratic. There's only one. It now fixes the quadratic. So let's do that. So how are we going to solve for a if we know that when x is 0, y is 3? How are we going to solve for a? Dave, put 0 in for x and put 3 in for the value of f of x. So this is like saying, if we translate this to function notation, f at 0 is equal to 3. Okay, so we put in 3 for the value of the function, we put in 0 for x. So 3 is equal to a multiplied by 0 minus 2 multiplied by 0 plus 3. All right? People see a yet?
Pretty sure we would have been dead by now.
What's that? No? Okay, so let's keep going. 3 is equal to a. Oh, we're in group 2, so we evacuate with group 2.
At least not group 3.
Yeah. So a multiplied by negative 2 multiplied by 3. So here, a is some number that when multiplied by negative 2 and positive 3 gives us 3. Yeah? Yes, a is going to be negative 1 over 2. Here's how I would do it. I do this, and so that gives me negative 6, right? So this is 3 is equal to negative 6 multiplied by a. Divide both sides by negative 6. Gives me a is equal to negative 1 over 2. There's my a. Okay. Therefore, the desired function is f of x is equal to negative 1 over 2 multiplied by x minus 2 over x plus 3. Okay? And this is a general application of the idea. If I have one equation with 1, 2, 3 unknowns, I have like a lot of possibilities. I have infinite possibilities. But as soon as I know one more thing, which is like one more point, I know the value of the function, I know my x, so the only unknown is a, and I can solve for that. One equation, one unknown, solvable. Solvable to a single solution. So then when I solve for a, by doing here a times negative 2 times 3 gives me negative 6 times a, okay, and that's equal to 3. I divide both sides by the coefficient, so I'm multiplying by negative 6, so I want to divide both sides of the equation by minus 6. 3 over negative 6 is negative 1 over 2, and that's a. So then I just input it in there. That's my function that I want. Okay. So now we can use that to solve some application questions in the world. I think like this is all we're going to do today. I think we're going to have to do the quiz tomorrow. That's what I'm feeling, right? There's good and bad in that, and the good and bad is you're going to have to do it on your own. I'm not here tomorrow.
They told us to go outside. Sorry.
Oh.
Yeah, we were told by the teacher.
Misinformation. Okay, so let's carry on here. Making connections. So we're going to now solve this type of problem. We have a highway overpass. It has a shape that's a parabola. Parabolas show up a lot in architecture. They're a very efficient way to distribute vertical load and to have a span over an area. It's a very efficient structure. It's more efficient than a semicircle. It distributes the load much better. So architects like them, bridge designers like them. They will often use parabolic arches to create heavy things that have an open space. So we have here our 0, 0, and that's one corner of the highway. The other corner of the highway happens here at 10, 0, okay? Because the edge of the highway is the origin, that's there. The other edge is 10 meters wide, so it's there. What's an equation of the parabola if the height 2 meters from the edge is already 7? So that's the point 2, 7. Okay, you can't see, maybe you can't see what I wrote down there, but that's 2, 7 there. So now I want the equation of this parabola. Can we find it? Can we find that equation? Is that possible? Yes, it's possible. So let's do it. Our first step was we copy out f of x is equal to some unknown stretch factor. I don't know that yet. Multiplied by x minus the first root. What was the first root? 0. So I just have x. Multiplied by x minus the second root. What was the second root? Yeah, we had 10 over here. Yeah, so I have this other root at the point 10, 0. So I have x minus 10. Notice that I have x minus the first root. The first root was 0, so that's just x. And then x minus 10. Okay? Now, I know one more point. Let's express this point, 2, 7, as a point. So that's 2 meters from the edge, 7 meters up. So that's the point 2, 7. So now I'm going to let xy equal to 7 to solve for a. So xy, so I put in 7 for the value of the function, and then I put in 2 for x. So I have a multiplied by 2 minus 10. Okay? All right? It's looking like a is negative. Should that surprise us? No, because this is an arch. It's like an umbrella shielding you from rain. You could go under the bridge to shield yourself from rain. All right, so now I just evaluate. 7 is equal to a multiplied by 2 times 2 minus 10. 2 minus 10 is Negative 8. Negative 8 times 2. A is negative 16 there. So A times negative 16. Usually I'd write negative 16A, but if I write it this way, it's still the same thing. So how do I now solve for A? Divide by what flavor of 16? Yeah, if I divide both sides of the equation by negative 16, I get my answer here. There's my A. A is equal to negative 7 over 16. There. So that's my A value that makes this true. Negative 7 over 16. Notice how clean this is as a fraction, how ugly it would be as a decimal. So try to keep your answers in fractions. Makes it easier. Now, let's input it in there, and that will be the equation that we're looking for. So therefore, the equation of the parabola, the equation of the parabola that outlines the bridge is, and then I write it down here, f of x is equal to, I have negative 7 over 16 multiplied by x minus 10. Note I don't really need this set of brackets. I could have minus 7x over 16 times x minus 10. And that would also define this parabola. There, done. So that's the lesson for today. Now, you know how to take 3 points, if 2 of them are the roots, and you can use 1 more point to define a parabola. And that can be very useful if you want to find out what is the parabola that models this basketball that bounces from 0 to 5 meters, and its highest point is this. You can now find the equations of these types of shapes that you'll see in nature, that you'll see in architecture, or that you'll see in business. So very useful skill to be able to model these things with equations. What can I use that equation for? I could use it to find the height at different points along this bridge. I could use that to determine if a truck has enough clearance to go under, given how wide the truck is. I can use that to find a good many other things. So yeah, very useful skill to have there. So thanks everyone for showing up for your learning today and solving these questions. Your homework, I'll just put it in the video, is in here. And there's a Delta Math assignment for today. I'll do a video about the Delta Math as well.